We have 9, okay, participant 9, should have 30, right? So I think it's quite clear that we have discussed on uh, the structure or the basic what we have for electrochemistry, particularly for voltammetry. Okay. All right. So I think I have discussed during the last lecture that we had, the discussion that we had is on the function of working electrode, okay, reference electrode, and counter electrode, as well as the function of supporting electrolyte. So these 4 elements are very important for voltammetry. And I also have introduced to you that voltammetry is similar to, if you learn physical chemistry, probably many years ago, you might have come across like galvanic cell, electrolytic cell. Okay, so this is what we call as electrolytic cell. Okay, and famous for example, water electrolysis. Yeah. Okay, so in electrochemical or voltammetry, uh, voltammetry particularly is, we would like to know an information about the analytes, whether is how much, as well as it can be watts or qualitative and quantitative based on current. Okay, so in general, if you look at the structure here, this is the whole set. In voltammetry, I don't know whether you will be doing any voltammetry work in your lab. I don't know, but the previous batch I did bring everybody and show them the potential stat and so on. But I'm not sure about this, your batch, because I'm no longer the coordinator. You need to have what we call as potential stat. Potential stat is the one that give the system potential, which is applied, giving the system potential, applying potential. So what happened is the potential, we can set whether we want like minus 0.1, minus 1, minus 1.5, or we can have positive 0.1 and so on. So we can set the voltage to be supplied to the system. Of course, this is where the control happening again, and then we have this 3 electrode system. Okay, this one I think I have discussed with you. This related to galvanic cell, and we don't discuss this in this subject because we want to focus on voltammetry only. Okay, so what happened here is you can see that the potential stat that I mentioned just now, the machines provide potential to the system and the current will be generated. Okay, so that is the basis of voltammetry. So potentiometry here, do not confuse potentiometry with potential stat. Potentiometry is a method, electrochemical method. Voltammetry is also electrochemical method. So potentiometry is an electrochemical method where there is no need for potential to be supplied. You don't need to supply potential. So the best example is your pH meter. So if you just put the pH probe inside the solution, you can know the value of pH. It's actually based on a potential difference between the solution and the pH probe. Okay, the system does not need to be supplied with potential, because the difference of concentration in the beaker where you dip the pH probe and inside the probe generate a potential difference. So I'm not going to discuss that. So that is potentiometry. But voltammetry is different. Voltammetry is an electrochemical method whereby that the potential has to be supplied. If there is no potential being supplied, there will be no chemical reaction. There will be no chemical reaction if there is no potential supplied. And the one that supply potential, it is called potentiostat. Okay, potential. Okay, the machine is called potentiostat. So I hope that please don't get confused. Potentiometry is a method. Potentiostat is a machine that's supplying potential. Okay, so now if you look at this reaction, okay, so ferrum 3 plus is being reduced because it receives electrons, producing ferrum 2 plus. You can see the oxidation number reduced from 3 plus to 2 plus. And if you remember your physical chemistry, this is this voltammetry requires you to use Nernst equation. So this is where Nernst equation comes in. I hope that you, because I assume that you have listened to this lecture, recorded one. So Nernst equation, if you look at here, this is what we call as cell potential. You have to do a bit of revision. Cell potential, and this is where the concentration of the analyte. So I'm not going to ask you to do calculation using Nernst equation, no. But at least you understand that there is a relation between cell potential and concentration. So that's how you use this technique for quantitative analysis. So it's not a common technique if you go to the lab or if you are working in industry, big industry, for example, that has machines. What you usually use is HPLC or GC. So it's not common that you use voltammetry technique to quantify things. It's not something common in industry. But now there are some companies starting to use like this voltammetry to study corrosion and a few other things, yeah, especially battery. Those who are working with battery probably using this technique as well to study the battery performance. Okay, so what is this? Yeah, what is this? So if you look at here, this is what happened. Ferrum 3 plus before any potential being supplied. Okay, so as I mentioned just now, if there is no potential supplied to the beaker, I hope that you can imagine these types of beaker. Okay, if there is no applied potential, there is no chemical reaction, meaning that there is no reduction, there is no oxidation can happen. Okay, so that is voltammetry because it requires potential for the reaction to happen. Now, if we supply potential, okay, specific amount of potential that suits the ferrum 3 plus, okay, now we can observe the changes or the reduction from ferrum 3 plus to ferrum 2 plus. So you can see that that's why the bulk concentration of ferrum 3 plus is decreasing because change from ferrum 3 plus to ferrum 2 plus. Yeah, okay. It's a simple reduction process from ferrum 3 plus to ferrum 2 plus, but it requires a potential, specific potential for that process to happen. Okay. So this is just telling about in order for the ferrum 3 plus, okay, receive 3 electron, producing ferrum 2 plus, sorry, no, 1 electron, sorry, 1 electron, ferrum 2 plus, okay. You have to do a bit of imagination that the ferrum is inside the beaker, okay. We are talking about ions moving here and there in the beaker. So in order for this ferrum 3 plus to receive the electron, okay, to be reduced as ferrum 2 plus, it has to move closer to the electrode. Okay. Okay. So if the ferrum 3 plus is too far away from the surface of the electrode, then it's difficult for this to happen. Okay, for the reduction or the electron transfer to happen. So that's why there are certain modification, okay, or measures or action that can be taken. One is, of course, we can do the stirring, okay, to make sure that the ferrum is closer, the ferrum 3 plus becomes closer to the electrode surface. Okay, yeah, this is called bulk solution. So this is where the ferrum 3 plus is situated, and it has to move closer to the electrode so that there is a transfer of electron. So stirring can also helps. And another one, okay, that I have just discussed with Daya, okay, if you remember the questions on the assignment that you must at least use what we call as conducting polymer. So conducting polymer is usually the one that helps. Yeah, this is the electrode, and you can put the conducting polymer on top of the electrode. So how does it help? Okay, to improve the electron transfer. Okay, we want this process, the reduction process, to be very efficient. If it is too slow or it does not happen in what we call rapidly, okay, then our detection will be very slow, and it might not be very accurate because there's a lot of ferrum 3 plus that is not be converted into ferrum 2 plus. Okay, so that's why one of the things that we can do is to put all sorts of current enhancement material, on top of electrode. So some of it, some example of current enhancement material is conducting polymer. And you also need to know why conducting polymer helps to enhance the electron transfer. Okay, so if it is all about chemistry, so if you have done some homework, what is the types, what are examples of conducting polymer? You will come across polyaniline, polypyrrole, okay, and there is P dot. I can't remember the whole name of P dot. But if you look at the functional group, of that polymer, you can find amine. You can also find a pyrrole group, okay, which with oxygen, and the P dot, I don't remember but you will find those lone pair electron, okay, because nitrogen, oxygen, they all have lone pair, right? Okay, so those polymers, they have this element of lone pair electron, and this actually has the capacity to enhance the movement of electron or the transfer of electron between the analytes and the electrodes. So that's how they, among the things that can happen that we want to have a better electron transfer that contribute to the sensitivity of the sensor that we are developing. So that's how basically they work. Okay, and this is what people have studied, okay, how the ions, how the ions move. So there is a bit of migration due to electrostatic attraction, mechanical motion is stirring, that's why you need to stir, and diffusion. Diffusion also is due to difference in concentration. So let's look at what happened here. This is, okay, an example of voltammetric analysis. So in here, we trying to detect the concentration of plumber. That's why it is X molar. You don't know. Okay, and this is the setup that you use. You are using platinum working electrode. Okay, you have argentum, silver, counter electrode. Okay, and this is reference electrode. Okay, so reference electrode usually is to stabilize the potential. We don't want the potential to fluctuate. So what happened here is, okay, this is also physical chemistry that you have probably learned before about the electrode potential value. Okay, so I'm not going to teach you the electrode potential value, why plumbum is being reduced, why, what about other ions, why other ions not being reduced. Okay, it's about value of electrode potential, so I'm not going to teach that, right? So consider this, that we are focusing on plumbum. Okay. Okay, so this is in the beaker. This is what, and in the beaker, you have plumbum 2 plus, and you also have K plus comes from the supporting electrolyte. Okay, the KCl is the supporting electrolyte. Okay, and this is the potential. Right, it's not, I finish up the battery. I have to use my hand. Come on. Okay, if you notice, okay, the voltage is negative 1.0. So this is what I mentioned about. You can choose how much potential that you want to supply the system. And it has to fit. It has to fit. Okay, this is suitable for plumbum. This is suitable for other materials. This one part of the research that usually we have to do to check on which potential is the best. So what happened here, you can see that there is also K plus, there is also PB2 plus being reduced, okay? So in here, there is a layers of K plus built up around the electrode, stop the migration of Pb2 plus, meaning that what does it mean is this will sort of things that we don't want to happen. Okay? We don't want K plus to be on the layer of electrode because this will prevent the migration of Pb2 plus, because what we want is Pb2 plus to be close to the electrode here. But instead, K plus is there because they have the same charges. They sort of repel each other. So we don't want this to happen. So this is another reason why we need to stir the whole thing. So to make sure that what we want to happen is the Pb2 plus to come to the electrode and being reduced. Okay, so this is the process that happens in voltammetry. And this is the nurse equation involved. Okay, so you can see the supply, the applied potential. Okay, the applied potential. And this is the concentration of the analytes. Okay, in this case is Pb plus 2 electron producing Pb plumbum in elemental form. Okay, so this is the basic. So if we are analyzing metal, it's quite easy because metal is already electroactive. Yeah. So, but imagine if you are trying to do DNA, antibody, organic materials like glucose, they are non-conducting. So it's very challenging when you are working with non-conducting organic material, but you want to do it using electrochemistry. But of course, there is a way to do it because electrochemistry is very robust. Because if you imagine you're talking about optical, let's say, optical meaning that the color change. So if you choose color change, let's say if you are working with blood, if you are working with blood, imagine that the blood is red. And then let's say whatever color change that you expect to happen will be interfered or will be covered by the color of blood. So that's why electrochemistry is very important because you can do a lot of modification on electrode, on the surface of electrode, to get a very good sensor, very sensitive, a very good, you can do a lot of things. And the one that usually interfere if you have ions in the sample. Okay. If there is colors, it's okay because it does not react to colors. But if it is color based, then you have a problem if your sample is colored. Okay. So for electrochemistry, this is the advantage. It's very sensitive because we are talking about current, and we're not talking about high current. We are talking about nano amperes current, micro amperes current. So the device now can detect the changes at micro amperes, at nano amperes. So this is very interesting technique. Okay. So again, I'm not going to ask you to understand all this, but if you wish to understand, you have to open up your physical chemistry notes, year 1. Those are in year 1. Yeah? So you can see that let's move to another one. Yeah, this is one of the equation. One of the equation apart from nurse equation. So this is another equation involving electrode area. Okay. Okay. So another thing, just now I mentioned about, you can do modification on the surface of electrode. Okay. So I talked about you can put polymer, conducting polymer just now. So those conducting polymer also can provide a greater surface area of electrode. In this case, we're not talking about the electrode getting bigger or no, but the working area of the electrode, meaning that if you calculate theoretically, if you calculate using these equations, then we can get higher electrode surface if you do modification. Okay, apart from using conducting polymer, you can use nanomaterial. So that's why if you read journals, you will find a lot of nanomaterials being used to modify the electrode in order to get higher current. Usually how it functions is the nanomaterial will provide greater electrode area. Okay, and if we can provide a greater electrode surface, here if you look at A, so it is directly proportional to current, right? You can see it is directly, if the surface area is greater, the A value is greater, okay, you can sort of get higher current according to this equation. Okay, so it's very important to try to improve the electrode area, surface area, by putting in modifying with potential polymer, nanomaterials. There are other sort of things that you can do to modify the surface. So this is what happened. Okay, all right. All right. So this is again the detail of what happened in electrochemistry. So more examples. Now we put potential applied on the system, on the working electrode. In this case, we are talking an analysis of cadmium 2+ using potassium nitrate as a supporting electrolyte. So what happened here is it should be moving, but I don't know. Oh, okay. All right. Okay. So once you put the right potential for cadmium 2+, so the cadmium now is being reduced, cadmium 2+ being reduced to elemental cadmium, which is cadmium, all right? And then you can see current start to increase, yeah? Current start to increase. This is where you observe, okay, how much, because this current, okay, if you like, right, put it in this where equation, there is a possibility that you can not here, not this equation, sorry. The nurse equation, you can also calculate the concentration, but in this case, okay, let's there's another equation actually easy for you to understand. All right, now, all right, okay. So here is the area where cadmium 2+ has not been converted to cadmium yet, because the potential is not enough. So once the potential is enough, okay, right? Let's finish it. Once the potential is enough, here you can observe the current increase. Okay, that's when the cadmium 2 plus starts to reduce to cadmium, because now it has enough potential to do that. Okay, the current at the working electrode continue to rise as the electrode become more reducing and more cadmium 2 plus around the electrode are being reduced. Okay, and next one, what happened is there is also limitation here. This shows that all the cadmium 2 plus has been converted. Okay, so that's why for voltammetry, the technique will give you two informations. One is quantitative. Yeah, because if you achieve this limit, you will get the value of ID. Okay, will and then put in the equation so you can calculate how much cadmium is there. But in this case, because we already knew the cadmium, but if it is X molar, for example, then you can calculate the quantitatively how much the cadmium in the solution, because it will has what we call as what is the name, peak potential or peak current, sorry. Yeah, this is what we call peak current. The maximum current it can be generated. Yeah, so that will give you the quantitative information on the amount of cadmium in the solution. So what about E half? Yeah, half potential. Yeah, so you can see that the half potential here, when we supply potential to the beaker, to the solution, we usually set a range. Okay, in here, let's say we start from negative 0.1 to negative 1.5, let's say here. It's not a single value, it's a range. So you can observe from here up to minus 0.4, there is no current generated. Only a slight small current, that one is what we call as residual current. It is not considered quantitatively. So up to 0.6, you can see there is a spike increase of current. And this is where what we get, what we call as, we can get the value of half wave potential. Half potential. Okay. Half potential is important value if we want to know qualitatively. Okay, in this case, because we already knew it is cadmium, probably what important to us is quantitative. So we can use the ID value. But if you are studying something you don't know, the E half or the half potential can be an indicator of what is inside the solution. Okay, it might not be that accurate like HPLC or GC, but it can give you some ideas that at 0.6, okay, what is the material inside the solution. So this is voltammetry. Okay, so this is called just now ID. ID, I don't know, we usually call it peak current, but it is here limiting current. It's current generated when all the analyte is finished. Okay, and then we have E half wave potential. That gives you the idea. For example, it might be cadmium, it might be mercury, it might be plumbum in the solution because they have their certain range of potential. Okay, right. So this is an example of like if it is HPLC, you have chromatogram, right? Chromatogram. But for voltammetry, you have voltammograms. So this is an example of results generated from voltammetry. You have voltammograms. So you can see if you have ferrum only, there is one half potential. But now, if you have more than one species, let's say you have more than one species, you can see that you're getting two half potential that responds to that specific species, because now you have two. In here, you have only one, which is ferrum 3 plus O2, from ferrum 3 plus O2. So you can see from the shape, okay? This one we'll just skip. So this is the sub technique under voltammetry. You have ampro, pulse voltammetry, cyclic voltammetry, which I will not discuss detail with you, right? Unless you want to study biosciences, or if you're interested in electrochemistry, then you have to take electrochemistry courses. All right? Okay, questions? I hope this will help you with the assignment. Can you understand basically electrochemistry, particularly voltammetry?
Yeah, doctor, like I
Right.
think a lot of recap to be done from previous what we learned. Thanks.
Okay. All right. So I think the second part of our discussion will be on optical. So please I think you have the lecture notes already. Did I put it in Putra Blast for optical?
Yes,
Yes,
I have.
Yes. Okay. Okay. Good. All right. So I think we should have a break. You also need to think about my question, whether you want a closed book exam, final exams, or you want an open book final exam. So I think the best way is we, do some voting, or you have consensus already? You never, or anyone has discussed this with your groups, or Daya for open book exam? I will try to do sort of voting in WhatsApp. So yeah, let's see. All right. So see you at 8 o'clock. Thank you so much. Please have the optical techniques ready. Yeah. All right.
okay, doctor, thanks.
Welcome back, everybody. While waiting for some of your friends, I actually assume that everybody has taken molecular spectroscopy. 5202. Correct. Last semester. Can I have a show of hands who's taken?
Yes. Yes,
Ah,
Prof.
yes, and anyone else has taken molecular? Shalini, have you taken the molecular spectroscopy last semester? Are you there? Lily, have you taken molecular?
I have not.
You have not.
Yes, I'm here. I have not.
You have not taken, yeah. Julie, have you taken molecular spectroscopy? Shirley,
Yeah.
you have taken last semester.
Yeah.
It's a CHM5202. I believe the one who taught is Dr. Emilia and Dr. Nadia.
Hello, hello, doctor. Can you hear me?
Yeah, Shalini. Have you taken molecular spectroscopy? Shalini?
Doctor, can you hear me? Sorry.
Yeah, I can hear you. Have you taken molecular?
Okay. No, I have not. I have not.
Okay, so
Haven't.
I just want to know in general because when we are talking about optical sensor, if it is chemical or biosensor, one of the techniques that we use is UV visible spectroscopy. Okay, so in order for you to understand, at least you need to have the, just like voltammetry just now, you need to understand about the basic behind the UV. Okay, so since I think quite a number who has not taken molecular spectroscopy, then you have to like focus on this discussion. Yeah. Okay. All right. Of course, the one that you have to. Why do I have this sometimes? All right. As I written here, have written here, you need to know about the terms chromophore, and this is something that you have learned during your undergraduates. So I know that this is something you have to do some revision, but it's just the name of the orbital because you have valence bond theory and molecular orbital theory. And in discussion of UV and UV-Vis spectroscopy, we are using the molecular orbital theory. Like antibonding, bonding orbital, non-bonding orbital. So I'm not going to like repeat what is antibonding, what is bonding orbital, or what is non-bonding orbital, but I'm just going to use the term for the sake of discussion. Okay, but you have to find out. Right. Anyone can tell us, especially for those who have taken the molecular spectroscopy subject, or you might remember the terms during your undergraduate study. What is chromophore? Anyone? Just whatever that you remember. Ahmed, do you remember?
Yes, teacher.
Do you remember the term chromophore? What is chromophore?
Not exactly.
Have you taken molecular spectroscopy last semester?
No, I haven't.
All right. Okay, anyone remember what is chromophore from your undergraduates or last semesters?
Yes, probably a molecule that absorbs the light or wavelength.
All right, molecules or compound, yeah? Because molecules are, what is molecules and what is compound? A compound can also be a molecule, but a molecule cannot be compound, okay? So you have to use the right term. So chromophore is a compound, okay? Right, that can absorb light. Okay, my next question is why chromophore can absorb light? Anyone? Just throw in your whatever that you remember.
Can you repeat the question, Doctor?
Yes, Ahmed. Can you repeat that? I don't get it. I don't get it.
Sorry, because I'm in the library, so I can't raise my voice.
Okay.
I said, can you repeat the question?
Why chromophore compound is a Sajita mentioned, but it can absorb light, energy, right?
Yeah.
So why chromophore compound can absorb light?
Because light is, as we know, is energy. So when the electron absorbs the energy, it must to transfer to another, or how to say it, another state, second or third.
Yes,
Like
you're
that.
talking about transition of electron. It's good. My question is, it's okay. I mean, if you don't answer, my question is, why chromophore? What types of compound that we refer as chromophore? That's okay. It's okay, Ahmad. So that's the purpose of this discussion. So for those of you who has gone through the molecular spectroscopy subject, then it's good for you to revise back. But for those of you who has not taken, you can always refer to your the subjects that you have taken during your undergraduates. Okay, so for, as I mentioned just now, for chemical sensor and biosensor, this is one of the technique, optical technique that we use to develop the sensor, because those spectrophotometer that you actually look at it as bulky, it can be miniaturized. It can be make it into a portable, small device. Yeah, all right. So here, what I'm going to discuss with you is some basics. Yeah? I'm not going to discuss back the whole molecular spectroscopy. All right, so the concept of electromagnetic spectrum. Okay, so there are a series of electromagnetic spectrum here. All right, and how do we know which one is like IR, which one is radio wave, which one is microwave, is through their wavelength and frequency. So when we're talking about ultraviolet or UV spectroscopy, we are talking about ultraviolet as well as visible region. Okay, so this is the region for ultraviolet, the wavelength, where ultraviolet is the one dominant, and this is the visible region, the wavelength where visible region can be observed. Okay, so I hope that you remember when we say electromagnetic spectrum, there's a lot of, there are many range which involve radio frequency, microwave, IR, near IR. Okay, but for UVV spectroscopy, we are talking about ultraviolet and visible only. So this is the region. All right, so this is the some terms, okay, that you have to be, you know, you have to make sure it is at your fingertips. What is chromophore? Because as Sajita mentioned, this is the one that absorb the lights. Okay, why? Because it has specific groups, functional groups, okay, that actually have free electrons. Then that electron actually absorb the lights, absorb the energy, and as Ahmed mentioned, it will be excited to higher states and so on, right? This is also chromes. So I hope that you remember what is pi. Okay, especially when you have double bond. Yeah, chromophore. Some of the character is you have double bond. So if you remember your organic chemistry, Double bond is what we call as unsaturated. Unsaturated. So where you have not to say free electron, but the electron can jump. So that's why when you have chromophore, it is that compound is considered as chromophore. They are they tend to absorb lights, okay, because they have what we call as free electron. Okay, so the electron can be excited. Right, this is the shift. Yeah, so this is when you observe later the UV spectrum or the visible spectrum. Okay, I will show you the example. This is where you can decide whether it has beta chromic shift, hypsochromic shift, whether it moves to longer wavelength or shorter wavelength. So this is just terms. But for you to classify, that's why I asked the word chromophores. Not all compound can absorb lights. There are certain compounds that can absorb lights, and there are certain characters that certain characteristic of compounds which we call chromophores. Okay, so that's important for you to identify which is chromophore, which is not. Okay, this is just telling about what is UVVs. So absorption of photon. Photon, I hope you still remember the term photon. Usually we say lights. And it has certain energy and frequency. Okay, E equal to H times frequency. H is Planck constant. Yeah. So photon is energy and it is related to frequency, wavelengths. Yeah. All right. So this is what photon is. And when electron is absorb the photon, which is the energy, that is what we call as electronic transition happens in the molecules. All right. So that's why you need to know this molecular orbital theory. This is MOT, molecular orbital theory. So after this, you go back and look at what is MOT. Okay. Because in valence bond theory, okay, let me valence, valence. Okay, in valence bond theory and molecular orbital theory, we are discussing the theory of covalent bond. Okay, how the electron is being shared in covalent bond. Okay, so in valence bond theory, you have the SPDF orbital, okay, atomic orbital, and then when they are shared in valence covalent bond, the orbital is hybridized. Okay, that will be a valence bond theory. But according to molecular orbital theory, the name of the orbital is no longer SPDF. It's no longer considered as atomic orbital. It is straightway considered as molecular orbital. So these two theory is different. Yeah. But they are trying to, the theories are trying to explain the covalent bond, how the electron is being shared in the covalent bond. So molecular orbital theory, instead of the name of the orbital that you are really familiar, which is S, P, D, F, okay, they name it differently in molecular orbital theory. It is called bonding, sigma, pi, there is sigma star, pi star, okay? Sigma star, pi star. So in molecular orbital theory, it is introduced as bonding orbital and anti-bonding orbital. Okay, so the one with star is anti-bonding orbital. The one with no star, sigma, and pi is bonding. So you can see this is the energy level. Okay, so the anti-bonding is of course higher energy, whereas the bonding is lower energy. So this is the transition of electron that can happen. It does not necessarily happen, but it can happen. So the transition of electron can move from sigma orbital to sigma star orbital, let's see. And this will require a lot of energy because you can see the difference is very high. Okay. And it also can happen from pi to pi star. So this is the level of energy required. And also this one. N is non-bonding or lone pair. Yeah, lone pair electron. So these are the transitions of electron that can happen when the compound is receive photon, absorb photon, and the electron is excited. Not the compound is excited, the electron is excited. Yeah. Right. Same information. This is the movement or transition of electron that can happen. And you can see that this is the information. Okay. Saturated compound, meaning that a compound that does not have double bond or triple bond. Okay, this is not common because it requires a very high energy. So this is the most common. Okay, and usually that's why we have unsaturated functional groups. Okay, right? So what does it mean as unsaturated functional groups? Means that the compound has double bond, minimum double bond, triple bond. Okay, that is unsaturated. And since I mentioned about the electron is free with the movement compared to the saturated compound, single bond. Okay, so you can see the transition of electron here is much common. Okay, I think my slide is not moving. Sorry. Why is my slide not moving? Hello, everybody. Sorry.
Sorry, Doctor?
I think my slide is not moving because, yeah.
Yeah.
Yep. It should be different slide, not the one that you observing right now. All right. Let me check why. Okay, let me check. Right. You are seeing the slide, the same slide just now, right? The
The two
molecule.
values bond here, the
Ah.
pi
All right.
sigma.
Why is not moving? Let me share again. Unshare and share. Yeah. Ah, I think the battery. All right. How do I close this one? All right. Connection fail. Just a moment, right? Okay. Just a moment. Should be out by now. I don't know. Yeah. Let me try to share from here. Okay, has stopped. Did you have stopped screen sharing? No. Just a moment.
Yes.
All right. Actually. What? All right. Okay, this is the one that I would like, I explained just now. Okay. Let me abandon this. Stop sharing. Okay. Let me open. All right. Just a moment. All right. Okay. Now you are seeing the new, right?
Yes, doctor.
All right. The new one, right? The with arrow green. Yeah. Is it?
Yep.
Okay. So this is the 4 types of transition as I mentioned just now. Okay. The one that I keep explaining just now was when the slide was not there. Okay. So you can see here, all right, that these transitions are not common because as I mentioned, saturated compounds, they have single bond. So the electron is not free. Okay. So it's difficult to happen. It requires a lot of energy. Whereas for unsaturated, so minimum of double bond, or you can have triple bond, then the electron is free and it can, of course, easier to excite, to be excited. So these are the 4 types of transition that can happen, but the one that is common is N to pi star, pi to pi star. Why? Because you can see that the energy is based on the difference of the level of energy. You can see the energy is low. N to pi star, pi to pi star. Okay. All right. So again, this is a type of transition. Why time transition is very important? Because that's the one that is being observed when you run UVVs spectroscopy or spectrophotometer. Okay, so this is the detail of the transition. Transition means that the electron can jump from sigma orbital to sigma star orbital. Sigma is bonding orbital, sigma star is anti-bonding. And this is the one that requires a lot of energy, which is unlikely to happen. This is also requires high energy, whereas this one is quite common, the one that usually happens, yeah? Okay, now, if you look at here, just now I mentioned about what is chromophore, okay? So if you, let me shut this down. This, right. So if you look at here, the compound that is characterized or categorized as chromophore, it requires the compound to have double bond, or at least it requires halogens. Yeah? Why? Because these halogen have free electron. Yeah, they have a lot of lone pair electrons. So these types of bond contain electron that is free. Yeah, free means that it is easy to move around. Okay, so when we excite the electron, okay, with certain amount of energy, depends on the lambda. If you look at here, this is of course the shorter the lambda, the wavelength, the higher the energy. Okay, so you can see this is the value of lambda requires to trigger this excitation of electron from pi to pi star and so on. Okay, right? So this is important. It's not like every compound can be considered as chromophore. So you have to look at the characteristic, the chemical structure of the compound, whether it has double bond, it has halogens. Yeah. All right. So here is also an example of chromophore. Okay, alkene, of course, it has one double bond. Here we have triple bond, and then we have carbonyl. So these are examples of chromophore. Okay, so let's say you want to do drug analysis, yeah, because chemical sensor is not just about portable device. You start with common benchtop spectrophotometer before we develop into portable device. Let's say you want to do, in the end, you want to do a portable machines or portable device to detect drugs, for example, or to detect what do you call it? Not poison, pesticide. You want to detect pesticide. Okay, let's say you want to detect pesticide usage in Cameron Highland in vegetables. So yeah, imagine you have, if you are doing the usual way, you have to bring back the samples to the lab. But let's say you have to do it quickly and you want something portable, a portable device to test the vegetables, whether they are using a lot of pesticides or they are using the normal permissible level. So you have to know about the pesticide structure, whether what kind of, okay, let's say you decide to use a spectroscopic technique first before you miniaturize the spectroscopy. So the pesticide actually usually contain this kind of chromophore, where you can do the analysis using UV region, ultraviolet region. So this is the example, because you know ultraviolet region is from 180 nanometer to 300. That is ultraviolet region. So if you look at a compound, there is carbonyl. So probably your analysis can work between 186. Okay, this is visible region already. 280. Actually, from 300 and above, you can observe the color. But if it is ultraviolet, that it is colorless. Yeah. So that's why identifying the compound of the analyte is very important to make sure you know what region of lambda that you are going to work with. If you have any question, please do stop me, because I'm not teaching molecular spectroscopy right now, but at least to get you understand when you are developing optical technique, you are looking at the molecular structure. Okay, first you need to know what is the molecular structure, whether you want to work at ultraviolet region or visible region. Okay, you have to know that. So this is example of isoprene. So isoprene is actually rubber. So now there is an effect if you like dissolve it in different solvent. Just now, if you look at this table, that's why the solvent is listed here, because the solvent will affect the lambda, the UV spectroscopy, UV spectrum that you will obtain will be affected by the solvent. So here, this is example of isoprene analysis. So this is the chemical structure of isoprene. And of course, from the structure, we observe there are two double bonds, okay? Here and here. And we know that this double bond, of course, it is something that is active in ultraviolet region, okay? Based on your study, you know, this compound is active in ultraviolet region. And when you do the spectroscopic analysis, meaning that you run the sample, the isoprene samples, in using spectrophotometer, then you observe the peak, which is at lambda max of 222. What does it mean here is this compound absorb, yeah, because this is absorbance spectrum, not transmitter, okay? So this is absorbance, okay? Spectrum means that this compound absorb energy at maximum lambda, maximum of 222 nanometer. Okay, so meaning that now if you have, this is not very confirmative, but you can at least run UV analysis to confirm certain compound, but this is not really really confirmative like HPLC or GC, but just to like give you some ideas, okay? So same goes, let's say you have similar structures like, you can see here, there is a bit of similarity, even though they are different compound, okay? You can see that they have a slight shift of lambda, okay? So whenever that the structures, there's a bit different of structures, then you have a shift in lambda. So again, I'm not going to teach molecular spectroscopy here, but at least you understand how optical technique works, because you can do sensor by using optical techniques, okay? Now, this one I will skip because you will learn in molecular spectroscopy what is shift and so on, because this shift can happen if we have conjugated. So what is conjugated, okay? This is conjugated, where double bond is actually alternates with single bond, yeah? All right, let me skip this. Solvent effects. I want to go to somewhere. Okay, this is the basic of UV visible spectrophotometer, spectroscopy. Spectroscopy is the technique. Spectrophotometer is the machine. Okay, for quantitative analysis, because most of the time when you develop sensor, you want it to be quantitative. Okay, so for UV spec, yeah, UV spectroscopy, we rely on Beer's law. Yeah, this is Beer's law. A is the absorbance, equal to molar absorptivity. B, the path length of the sample, is how we measure the sample, and C, the concentration. So the concentration is the one that we wish to know. Okay, how much? Quantitative, right? So this is, of course, when you do spectroscopy, UV spectroscopy, you use cuvettes, but actually you don't have to use cuvette. There's so many other ways to put the sample into the spectroscopy, into the spectrophotometer. So Beer's law also is not covered, but should be used. Yeah? You have to construct a calibration plot. Okay, those things that you have learned some of you has learned in molecular spectroscopy. So this is the basic instrumentation for UV. You have light source, you have a monochromator, which select the wavelength. And this is a sample you wish to analyze, the one that and the light in it. Okay, for example, I mentioned drug, I mentioned pesticides, because those are organic compounds that contain chromophores usually. And you can have the detector, means that you will get absorbance, the absorbance spectrum just now. And then you can analyze the absorbance spectrum in terms of quantitative, might be qualitative as well. Okay. All right. I want to directly, so I'm not going to also talk detail on the engineering or the parts for UV, because you will learn this in molecular spectroscopy. All right, this one. Okay, right. So this is the technique. Once you have done the UV spectrum analysis, you have to construct the calibration curve. But nowadays, the machines are very intelligent. You can just like generate all the results straight away. You don't have to plot your own calibration plot. Okay, this one also will not be covered. Standard addition method. This is the one that you will learn probably later. All right. Okay. So this is an example of analysis of titanium oxide, dioxide. Okay, looking at the sunscreen effect. Okay, the content in the sunscreen. Okay. So yeah, because it does absorb lights, so that's why it is used in sunscreen. All right, SPF. Okay. Okay, let me move to one last one. Because now it's already okay, 8:36. Fluorescence. Okay. So there is another technique that also is very important in development of sensors, optical sensors, which is fluorescence. Just now is UV visible spectrophotometer, and this is fluorescence. So what's the difference between fluorescence and UV ultraviolet or visible and visible region? Yeah. So this one, I think it should be known already to you because we mentioned just now about chromophore, and in chromophore, well, the electron is free. Okay, so it can absorb energy, and the electron is ground state level, can also be excited to higher state energy. And when it goes back, yeah, when it goes back down, I don't have the simple picture. Okay, all right. So this is the ground state, and then electron is excited to probably the first energy state. And then when it goes down, relaxation, it will transmit energy, it will emit energy. So that one, again, I'm not going to discuss in detail you have to revise back if you have taken molecular spectroscopy, or you have taken during your undergraduates the excitation of electron and the relaxation of electron that emits energy. Okay, the UV spectrum that you observe is the process of when the electron absorb and excited to higher state energy level, and this happened at specific wavelength. Okay, again, I'm not going to discuss about the energy is quantized. I'm not going to discuss that. But what's the difference between UV, visible, and fluorescent? Okay, so if you look at here, if the electron is excited and straight away goes down without any another process, you will get UV or visible region. But if you have like this one, there is internal conversion and then it goes inter-system crossing. Okay, this results in fluorescent. Okay, so if you have internal conversion, it does not straight away goes back to lower energy. It goes stage by stage. Then you will have what we call as fluorescence. Okay, fluorescent. So this is the biggest difference in production of UV spectrum and fluorescent spectrum. So this Jablonski energy diagram is very important for you to understand. Okay, very important to you. Very important for you to understand how the electron is excited, with which process produce UV vis spectrum or process, or which will results in fluorescent spectrum. Okay, all right. So you please read on this Jablonski energy diagram, because I mentioned this is not the subject where I teach the Jablonski. Okay, but this is the difference. So fluorescence is very sensitive compared to UVVs. Okay, so if you're working with fluorescence compound, using fluorescence spectroscopy is very useful, because they will give you, the machine will give you better reading compared to UV-vis spectroscopy. Yeah, right. So this is, I'm just going to show an example of fluorescent base. Okay, right. So you can see this is some of the compound, yeah, that can fluoresce. Yeah, you can see they are actually also considered chromophore. Okay, but if you run this in UV vis spectrophotometer, you will get very low spectrum. Okay, but if you run this compound, the same compound, in fluorescent spectrophotometer, you will get a better, higher spectrum. So that is why fluorescent spectrophotometer is very important, because it will give you a better reading. Right. Let me. Okay. Again, this is the same thing. The electron transfer. But I'm going to show you the. I hope that I have. Okay. Sorry. Right. So if you look at this purple spectrum, okay, this is UV or visible, UV visible. I'm not sure because there is no wavelength here. Okay, so the same spectrum, the same compound, okay, it is run under spectrophotometer, UV spectrophotometer machine. You will get this spectrum. But if you run in UV, in fluorescent spectrophotometer, you will get, actually it is supposed to be higher, okay? Higher spectrum, okay? So there is a difference in terms of wavelength, okay? You will have a slightly shifted to the longer wavelength. So this is fluorescence emission, and this is UV vis absorption. Okay, all right. Let me straight away. Okay, so this is examples of fluorescence and absorption. So this is the same compound, for example, is alizarin, run by spectroscopy, UV spectrophotometer, and this is run by fluorescent spectrophotometer. And usually, okay, the spectrum is higher. The emission spectrum of fluorescent is higher. Okay, all right. All right. This is another, again, this is also an example, absorption and fluorescent spectra of compound. I don't know what is this compound. Usually protein, yeah, protein, or they can be fluorese compound. So you can see that what we usually observe, fluorescence will give you a better sensitive spectrum that you can analyze. Okay, so I'm not going to discuss what is Stokes shift and all that. Please, you'll be learning that in molecular spectroscopy. All right, so questions. This usually requires a few weeks to discuss on UV and fluorescence itself, but this is an express express version. Okay, questions on this? No questions.
No, doctor. Bro. Sorry.
Okay, it's okay. So I hope that you can revise back. Okay, look at the video or whatever that I have shared in Putra Blast. I'll also be recording this. Okay,